Morning. As you've seen, we have 3 French speakers, so we decided to do everything in French. And also, I think the first speaker doesn't need any introduction because maybe 1/3 of the audience actually learned probability theory in courses by Jean-Francois, and people disliked his lecture so much that they turned away from probability, right? But everybody's here. Anyway, so it's a pleasure to have Jean-Francois speak his first lecture this morning, and we'll talk about first passage population and local modifications of maps.
Okay, thank you, Wendelin, for the introduction. So I first need to apologize because I changed the title of my lecture, and also the abstract is not quite correct, in fact. But still, it will be related to what I said in the abstract. Okay, so I'm not going exactly to describe the results that Timothy Budd mentioned on Monday, so I'm sorry for that, but there will be some connection. Okay, so this is joint work with Nicolas Curia. So the basic idea is to look at large random planar maps, and instead of looking at the graph distance, as one usually does, looking at modified distances. So I'm going to describe this in the introduction of the lecture, the kind of modified distances I want to consider. But essentially, the goal is to show that for random planar maps, while in large scales, these modified distances behave like the graph distance, up to a multiplicative constant. Okay? So one case I will consider will be the case of first passage population distance. I will describe that in a moment. So the kind of behavior we get for planar maps is quite different from what one expects for deterministic lattices. Okay? So for deterministic lattices, it's not expected that the first passage population distance behaves like the usual distance. Okay? So, well, to start with the introduction, essentially I'm going to be interested in large triangulations or quadrangulations. And in fact, by large, most of the time I will mean the infinite one. So I'm going to consider the UIPT, which is the uniform infinite planar triangulation, which was introduced by Engel and Schramm in 2003. And okay, I could also consider, but okay, I will not deal with that case in this lecture. The case of the UIPQ, the uniform infinite planar quadrangulation. So I do not recall the definition of these objects, but just in one sentence, the UIPT is what you get if you consider the local limit of, in the sense of local limits of graphs, of uniformly distributed rooted triangulations with n faces. Okay? You let the number of faces tend to infinity. You take a local limit, and in the limit you get this infinite random lattice, which is the UIPT. So this is supposed to give you an idea of the UIPT near. There is always a root vertex, which I denote by rho here. Okay, so near the root vertex. Okay, so I will write DGR always for the graph distance, the usual graph distance on this object. And as I said before, I'm going to consider modifications. So modified distance I will generically denote it by d mod. So I want to first to give examples of the kind of modifications I'm going to consider. Okay. So the first one, maybe the perhaps very natural one, is let me call this A. This is too big. So the first one will be the case of the first passage population distance. Okay, so what do I do for that? Well, I assign to every edge of my planar map a weight. So in an independent way. So these are IID weights. So let's call them WE to the edges. Okay, so each edge carries a weight. Maybe this is the edge E, this is the weight WE. Maybe we have WE prime for this edge and so on. Okay. And so the edges are non-negative random variables, and you can think of them, if you want, as the lengths. We assign a length to every edge in our graph. Okay. And then we can define an associated distance. Okay. So what I denote by dFPP of V prime. So between two vertices V and V prime. So maybe V is here, and maybe I don't know, maybe V prime is here. Okay. And what is this distance? Well, it's just, if you want, the minimal length of the path between V and V prime. But of course, we measure length now using the edge weights. Okay, so in fact, the minimal total weight on a path between V and V prime. Okay. Okay, so that's the first example. Okay. Well, in fact, we can do other things. So something we can do is look at the dual graph of the graph we start from. Okay. So this is what I explained here. So let's say B. We're going to look at the dual graph distance. So, well, each time you have a random planar map, like this one here, you can define its dual. Okay, it just means that you look at the red graph, which is represented there. Okay, so you put a red vertex inside each face of the original planar map. Okay, and each time you have two incident faces, like this one, you draw an edge here, red edge, okay, dual to the white edge separating the two faces. Okay. So in this way, you get the dual graph. Okay? So again, you can consider, if you want here, you can denote by M star the dual graph distance. Okay, so you may say, well, in fact, this dual graph distance is not defined on vertices of the original graph. It's defined on vertices of the dual graph, that is on faces of the original graph. So this distargia is not defined, of course, on the same set as the original graph distance dgr, but still you can compare them. You can, well, for instance, you can compare balls, which I will define in a moment. Okay, so really you can make sense of a comparison, an asymptotic comparison of these two distances. Okay, so there is, in fact, an interesting special case in which one wants to combine B and with the first passage percolation distance, which is related to what people call the Eden model. So this, in fact, the first passage percolation distance on the dual, so not on the original graph as I was describing there, on the dual graph, with edge weights that are exponential, say with parameter 1. Okay, so why is this related, in fact, to the Eden model, to the classical Eden model? Well, the reason is that if you, let's simplify a little bit. Consider the growth of balls for this first passage percolation distance. So essentially, imagine that at a given time, you obtain a ball like this. So I'm cheating because there should be holes inside. Just say the ball is like this, doesn't matter. So how is the ball going to grow when you increase the radius? Essentially, well, you have a dual edge corresponding to each of the edges here on the boundary. And with each of these dual edges, you have an exponential clock, and they are all independent. And when the first of these exponential clocks rings, it means that we discover the triangle, well, the face, which is more generally, or the triangle if we are in the UIPT, which is incident to this edge and not already in the ball. Okay, so maybe it's this edge here which comes first, and so we add this one. Okay, so because of the properties of exponential random variables, well, the edge that will be discovered here is distributed uniformly over all edges on the boundary. Okay, so what we do, if we look at the growth of balls, say at each step the ball changes. What we do, we choose an edge uniformly on the boundary, and okay, we add the face incident to this edge. Okay. Okay, so maybe a last case that one can consider is the case of Tut's bijection. Okay, and okay, so Tut's bijection is a bijection between general planar maps, say with n edges, and quadrangulations with n faces. Okay, so here I start, while in white I've represented the planar map. And how do you construct the associated quadrangulation? Well, you just put additional vertices, yellow vertices, one inside each face, and you connect each yellow vertex here to all vertices, I should say to all corners, in fact, of the face in which it is contained. Okay? And the collection of the white vertices, the yellow vertices, and the yellow edges gives you a quadrangulation. And okay, this is indeed a bijection. Okay, so here you may want to compare now the graph distance on M with the graph distance on Q. Okay. So what do I mean by comparing? Well, the general idea will be to say that in large scales, so maybe I can write it here. The goal that in large scales, let me try to make this more precise, the modified distance behave like a constant times the graph distance. Okay? So what do I mean by that? Okay, so well, to give a precise meaning and to state a result also, I will introduce balls. So I look at any R positive. I will first denote by B of R. This will be always the ball in one of these models for the graph distance. Okay, so okay, there are several ways of defining it, but here it's convenient to decide that the ball is a union of all faces incident to a vertex at graph distance strictly less than R from the root. Okay, so this is the ball for the graph distance. I can also define, of course, a notion of ball for the modified distances. So I will write these balls for the modified distance in this way. I'm putting the distance here in index, and it's defined in the same way. So, of course, when I deal with the dual graph distance, or in this case here I had the distance on the dual graph also, I can also define the ball. Just it's even easier. I just say it's a union of all faces at distance less than R from the root face. Okay, so it also makes sense if I have my distances on the dual graph. Okay. So in this lecture now I'm going to deal, in fact, essentially with the case of the UIPT. Okay, so unless otherwise mentioned, I will deal with the UIPT, and in fact I will deal with the type 1 UIPT. So type 1 means that I allow, it's like in this picture, I allow loops like this one, or I allow also multiple edges. I should have one here somewhere, here. Okay, so I allow loops and multiple edges. Okay, so In fact, the techniques also work for the type 2 UIPT, but I will consider this case here for simplicity. Okay. And did I forget something? Okay, so I will deal with the cases I have mentioned here. Well, mostly I will deal with the first case, and I will make an assumption on the weights. So I will assume that the weights are bounded above and below by positive constant. Okay, so this is probably not necessary, but just to simplify, and we have written the details in that particular case, in fact. Okay, so the theorem that we get, so it is concerned with this case and with any of the modified distances I have introduced there in A, B, and C. Of course, not in D, because in D I should deal with quadrangulations. But so in cases A, B, C, there exists a positive constant C0 such that, well, asymptotically, we have this property here. So I will state it in terms of balls. I will say that essentially the ball with the graph distance, with respect to the graph distance, is almost equal to a corresponding ball for the modified distance. So more precisely, I will look at the event that a ball for the modified distance of radius r is contained in the ball. So when I say nothing, it's the ball for the graph distance. And here I have to divide by C0. I put something slightly larger than 1 over C0r. On the other side, something slightly smaller. Okay? And I say that the probability of this event tends to 1 as r tends to infinity. Okay? So asymptotically, balls for the modified distance, well, are very close to balls for the initial graph distance. Okay? So this is essentially what we want to get. Okay, as I mentioned before, well, so this works here for the first passage percolation model. And, well, as you probably know, if you look at first passage percolation in deterministic lattices, like Z2, for instance, you really don't expect something like that. Okay, so you expect different behavior of balls. Okay, but in a sense, here balls in the random planar maps, well, there is more isotropy, if you want, in random planar maps. So there's a kind of averaging in all directions, and the consequence is that, well, you still get the same balls even when you do the modifications of the distance. Okay, okay, so maybe you can forget about this one, because I'm not going to deal with that case here. So just for motivation. So you can derive, in fact, from this result. So this is concerned with the UIPT, as I mentioned, but in fact, we can derive consequences also for asymptotic behavior of finite large triangulations. Okay, so let me mention a consequence, which is not a direct consequence. You need to work with it. So I write, say, script capital Tn for uniformly distributed rooted triangulation with n faces. So n has to be even. And well, one of the results of convergence to the Brownian map say that if you look at the vertex set equipped with the graph distance, okay, if you normalize it properly, so the proper normalization is by n to the power minus a quarter. You have a constant which is 6 to the power a quarter here, I think. And this converges in distribution at n tend to infinity to the Brownian map. While in the Gromov-Hausdorff sense, as we saw several times in this meeting. Yeah, sure.
An annealed result?
No, it's annealed. Okay. You really look at the probability. Yeah, it's annealed. Okay, so we have this convergence result to the Brownian map, and essentially because of the fact that we know that the first passage percolation, so I consider this case here, we look at the first passage percolation model, well, again under this assumption, and now on the finite triangulation, because the first passage percolation distance behaves like the graph distance, well, I said it, of course, only for the balls centered at the root, but, well, this gives you enough information, in fact. You can also obtain that you get a similar result if instead of the graph distance, you consider the first passage percolation distance. Okay, so some work has to be done, but this can be viewed as a consequence of the previous theorem. Okay, so it gives you one more class of discrete models, in fact, well, you don't consider now the graph distance, but a modified version, which again converge to the same limiting object. So it's a kind of confirmation of the universality of the Brownian map. Okay, so what about this constant C0 here? Well, as you will see, I will try to explain the basic idea of the proofs. In general, C0 comes from a subadditivity argument. Okay, so there is little hope in general to compute the constant C0, but in particular cases, it's possible to do it. Okay, so I just mentioned this here. Well, of course, this is related to the lecture of Timothy Budd on Monday, who was explaining how to compute exact values of the constants, well, assuming that we have this behavior of distances. Okay. So, for instance, what we can get is in the case B, so the case of the dual graph. So I'm still in the UAPT. Okay. Okay. Then we can find that C0 is equal to 1 plus 2 square root of 3. And in the case C, which is the case of Eden model, if you want, again for the UAPT, get that C0 is 2 square root of 3. So, in fact, why can we compute the constant C0 in these particular cases? Well, the reason is that we have other results, more or less independent of this one, which gives us the behavior of the volume of balls. Okay. So, in fact, it's not really the volume of balls that we consider, it's the volume of hulls. Okay, so I should maybe immediately introduce what I mean by hull. Well, as I mentioned before, when you look at the ball of radius r, typically the complement of the ball is not going to be connected. So typically in the complement of the ball, you will have holes like this. Okay? Okay? In these models. Okay? The hull is just what you obtain if you fill in the holes. Okay? So this is the ball, and if you want the hull, which I will denote by b dot of r like this, well, it's the same object. Would say, except now you've also included the holes. Okay, so if you prefer, it's a complement of the unbounded connected component of the complement of the ball. Okay, just the ball where I have added the holes. Okay, so why do I mention that? It will play an important role later, in fact. But also here, what we can do for instance, for the Eden model here, for this first passage percolation distance with the exponential age weight, we can compute, well, we can determine the asymptotic behavior of the volume of holes. Okay, so we have, in fact, a convergence in distribution, which is saying that r to the minus 4 times, well, let me consider first the case of balls for the graph distance. Okay, so I look at the corresponding hulls. Okay, this converges in distribution towards a certain limiting random variable u, and we know exactly what u is. we have an explicit Laplace transform for U. So this is something we know. And it's possible to derive a similar result when you look at balls for the Eden model. So we look at the balls for the modified distance. Okay, so this is for case C here. And if we want to get the same limiting random variable, we have to multiply here the radius by 2 square root of 3. And then we get a convergence in distribution on R tends to infinity. And the way these results are proved, in fact, it was already mentioned in the talk of Timothy Budd on Monday, it's using the pilling process, in fact. Discovering step by step the uniform infinite planar triangulation and doing this in such a way that we discover successive balls here or successive balls for the Eden model in the second case. Okay? So of course, this constant here must then be the same as the constant C0 which appears here. Okay? So it's a trivial observation that if we have this property, the same property holds also for the hulls. Okay, so this is the end of the introduction. So okay, it was quite long. I will try now in the second part of the lecture to give you an idea of the proofs, because it's interesting to see the kind of techniques we are using. Okay. So I should mention that it's really a work in progress. So we have written the details for the cases I've mentioned, but we think that the techniques can be applied to more general situations. Any question at this point? Okay, so I will come to the second part. And now, this is the important thing. So, this is the second part of the lecture. I'm going to deal with what I call the structure of layers in the UIPT. And this is very much related with the work by Maxime Krikoun around, I think, 2005. Okay. Although he was not considering exactly the same model as we do, but okay. Still there are some ideas that come from this work, definitely. Okay, so what I'm trying to do, okay, I'm considering, as I said before, I'm considering this object, type 1 UIPT. And maybe I can just erase that now. It's not so important. Before I deal with the modified distances, I need to have more information about the geometry of the UIPT. Okay, so in this section, second part of the lecture, I'm not going to deal with modified distances. So I'm just going to deal with the UIPT and try to understand a little bit the structure of hulls or of layers. Okay, so what do I mean by layers? Okay, so I'm going to fix here k smaller than L. I'm going to look at the difference between the hull of radius L and the hull of radius k. And certainly I view this as a, well, trivially as a union from j equals k plus 1 to L of the difference between the hull of radius j and the hull of radius j minus 1. Okay? And these are what I call the layers. Okay? So, well, here on my picture, well, inside the small blue cycle, here this is supposed to be the hull of radius k. Okay? And the exterior blue cycle is the boundary of the hull of radius L. Okay? So in between I have other blue cycles. So this corresponds to the boundaries of these hulls, b dot of j. Okay? Well, this is what I have written here. Okay? So the layers, if you want, are the parts of the UIPT between two successive blue cycles. So I have one layer here, another here, and a third one here. So in my picture, L is equal to k plus 3. Okay. Okay, so I have these layers, and of course, in between, okay, in each layer, I have lots of triangles. Okay. But I'm not going to consider all these triangles. So I look only at the yellow triangles. I don't know if you can see very clearly. the yellow triangles, I call them J triangles, okay? So for some J between K and L. So a J triangle is a triangle that contains an edge. Take this one, for instance. It contains an edge of the boundary of the hull, say of radius J here. And it also contains a vertex that belongs to the boundary of the hull of radius J minus 1. Okay, so it's very easy to see that, well, in fact, each edge here of the boundary of the hull of radius J is incident to exactly one such triangle. Okay? So if you want, J triangles are in bijection with edges of the boundary of the hull of radius J. Okay, so these are all the yellow triangles there. And of course, I do not get all the triangles if I look only at the yellow triangles. So there are other triangles in the shaded part which are there. Okay, and essentially, so of course I didn't want to have a picture too complicated, but in each such shaded part, I call these the holes, if you want. I may have many triangles. Okay, for instance here, okay, I may have this. Okay, something like that, but I can have something much more complicated if you want. Okay, okay. So I have, if you want, inside each hole, each shaded part like this, I have a finite triangulation with a boundary. Here, for instance, it's a boundary of size 4. It can be any size. The size of the hole can be arbitrary. Okay. So the important thing I want to stress now is that there is a tree structure hidden in this picture. Okay. So there is a genealogical structure, say, relating all the yellow triangles. So it's if you want, a combinatorial argument. And well, here I prefer to interpret this genealogy by saying that the vertices in the forest I'm going to consider will be all edges in the boundaries of the hulls. Okay, so I will define a forest whose vertices, well, I should say first, roots are the edges of the boundary of the exterior, well, the exterior boundary, so the boundary of the hull of radius L. So maybe I will put them in red on my picture here. So this will be, I will have one such vertex for each edge of the exterior boundary. So this will be the roots of my trees, if you want. And the vertices in the forest will be all edges of now the boundaries of the hulls, but for all hulls now of radius J for J between K and L. Okay? So if you want, I will have now again, okay, I can put here on each edge, on each blue edge, if you want, I put a red vertex like this. I do this at every stage. Okay, so these are all the vertices of my forest, but now I need to decide to draw the edges of the forest, if you want, to define the genealogical structure. And this is explained here, how I define the genealogy. I say that an edge E of the hull, of the boundary of the hull of radius J minus 1, so take, for instance, this edge here, this one here, is a child of an edge of the boundary of the hull of radius J. If when I move, okay, I'm going to move around the boundary of the hull of radius J minus 1 in clockwise order, starting from this edge. And the first time I meet a yellow triangle, so it will be this one here, okay, I say that, well, this yellow triangle contains exactly one red vertex. I said that this vertex is the parent of this one. Okay? So I put an edge like this. Okay? Similarly, for this vertex here, when I move around here, the first yellow triangle I meet is this one. Okay, so I draw an edge like this. Okay, so this one has no child. I go a little faster now. This one has just one child, which is here. This one has no child. This one is going to have two children. This one and this one. and so on. And this one has no child. This one has exactly one child. Okay, and here it's a bit more complicated. This one has no child, and this one has two children, say, for instance. Okay, so if you want, I wrote here, I've drawn all edges corresponding to the first generation of my forest. Okay, I continue this way. Maybe I'm not going to draw all edges, but for instance, this one will be related to this one to this one, and so on. This one here, etc. Okay? And for instance, this one is related to this one. No, it is a mistake. Sorry. This one is related to here. I have to move in clockwise order and to look at the first yellow triangle. So it's here. Okay. And so on. Okay, so I don't draw all edges, okay, because it would be too long. But you see that you get, in fact, a forest of trees, which describes, if you want, the configuration of yellow triangles. Okay. So why is this interesting? Well, in fact, we can completely describe the probabilistic structure of this red forest. Okay, so here is a proposition. So let's say proposition 1. Okay, so maybe I need some notation. The number of edges of the hull of radius L will be denoted by PL. If you want, it's a perimeter of the hull of radius L. So it's a number of edges you have here, so it will be the number of trees in my forest. Okay, so proposition, I start from a deterministic forest. I call it τ1, τ1 to 2 to p, be a forest with height L minus k. Okay, and so well, this red forest is going to have a height which is exactly the difference between L minus k. Okay, so in fact, easy to see that the maximal height you can get is exactly the difference between the radius of the small hull and the radius of the large hull. Okay, and I require here that I have also q vertices at height L minus k for some q. And okay, so I will give a name to this forest. So this forest I will call it τ1, script capital T1, script capital T2, script capital TPL. Okay, so PL is the number of roots, it's the size of the boundary of the big hull. And so I look at the probabilities that my forest here is equal to a deterministic forest. And it turns out, well, in fact, I need to condition on the size of the boundary of the small hull. Okay, so I condition on the size here of this boundary here. How many? Here I have 6, for instance, edges on the boundary of the small hull. So this is the perimeter of the small hull. And so the explicit formula is just quite simple. It's h over p over h over q times a product over all vertices here of the trees τ1 to p. In fact, I don't look at all vertices. I look only at those vertices which are at a height strictly less than the height of the forest. Okay, so I should put here v strictly less than L minus k. So L minus k. So I omit the vertices at maximal height, if you want. And then this product, I have theta of CV. So now I should say what these objects are. So CV here is just the number of children of V. Theta is an offspring distribution. And it can be computed explicitly. So here I just give its generating function. So sigma of theta of n r of n is equal to 1 minus 1 plus 1 over square root of 1 minus r minus 2. It's a, in fact, well, it's a very nice Austrian distribution. Okay, I don't want to say too much about that. And the last thing, what is this function h here? So h of p is just 4 to the power minus p, the binomial coefficient to pp. Okay. So maybe let me comment a little bit about that result. Essentially, we do not have this term here. This is really what you get if you have a forest of Galton-Watson trees. Okay. So this is telling us that my red forest here is very closely related to a forest of independent Galton-Watson trees. Okay. So T1 TPL is close to a forest of IID Galton-Watson with Austrian distribution theta trees. Okay. Well, it's not, of course, it's close. It's not exactly equal, and in particular because we have this additional factor here. But this factor is not, okay, can be also understood quite easily. This function h here corresponds, in fact, it's an easy calculation, to the stationary distribution for the Galton-Watson. Okay, maybe h corresponds to the stationary distribution for the Galton-Watson process with distribution theta. Okay. So, in fact, this can be seen also from the fact that if you sum the right side over all possible choices for tau 1, tau p, well, you have to find 1, of course, because if you take all possible choices here, this has to be equal to 1, and this is really the fact that h is a stationary distribution for the Galton-Watson process with Austrian distribution theta. Okay. Okay, so maybe I will not say more about that, except, I have to think something more. Here I have completely described, well, the law of the red trees. I mean, it describes the law of the configuration of yellow triangles. Okay, but now I should say what do we have in the holes? Okay, so well, this is not complicated. The holes are filled in by, I think, what Angel and Schramm call free triangulations with boundaries. Okay, so as I said before, each hole here has a boundary of a certain length. For instance, this hole has a boundary of length 3, this one has a boundary of length 4. But okay, there is a way of defining random triangulation with a boundary of fixed length. This is what I call the free triangulations. It's just saying that the probability of a fixed triangulation with, well, of course, with a boundary of the prescribed length and with n inner vertices is proportional to, I think here it's 12 times square root of 3 to the power minus n. Okay, this is, okay, maybe I don't say more about that. It's the way of, canonical way of defining these free triangulations. Okay. So now what are we going to do with this? Well, now the next step, so this was the second part. The next step is to say, well, essentially I'm interested in large balls. Okay, I still have my theorem here, r tends to infinity and so on. So here the boundary is going to become very large. So I didn't mention that, but it's not hard to prove that, for instance, the perimeter here of the hull of radius L, okay, PL, tends to infinity almost surely. And so the boundary is going to become very large. So essentially the configuration of yellow triangle that we get here will be close, in fact, to a certain half-plane model, which I'm going to describe now. Okay, so this is the third part of the lecture. The half-plane model. Okay, so now it's a different picture. So in fact, I'm looking at the lower half-plane. So if you want here, I have the line corresponding to the vertical coordinate 0, -1, -2, and so on, -3. Okay, so I call these lines L0, L1, L2, L3. Okay, so on each of these lines, I have vertices, which are the points with integer coordinates. Okay. And now I look at the configuration of yellow triangles. Well, it's very similar to what we had here. Okay, so each time I have a horizontal edge here, it's incident to a certain yellow triangle whose third vertex belongs to the line just below the edge I was considering. Okay. So it's just the same picture as here, if you want, for the, except that now the boundary is infinite. Okay. So I have this configuration, and okay, now how do I choose a configuration? Well, I can play the same game as before. I can say that such a configuration is coded by a collection of trees. So again, as before, I put like this red vertices everywhere. Well, one red vertex for each horizontal edge. And now how do I define the genealogy? It's exactly the same as before. Okay, I start from, for instance, from this red vertex here. I move in this direction to the right, corresponds to the clockwise order before. And I look at the first yellow triangle I meet, is this one. So I draw an edge between these two vertices. One like this, so it's easier to draw in this picture. Two like this, and so on. Okay, so for instance, this one will be here. This one will be here. Okay, this is for the first generation, and I continue. Okay. And then I will have this. And so on. Okay. So for instance, you have this here. All these three here, for instance, are going to be connected to this one, and so on. Okay, so now the point is that I choose my yellow configuration, my configuration of yellow triangles, in such a way that the red trees are IID. So I want the red trees to be IID theta Galton-Watson trees. Okay, so IID Galton-Watson trees with Austrian distribution theta, which is specified here by the generating function. Okay. Now I have, of course, an infinite collection of such trees. Okay, but still I can make sense of the configuration. And I say that in some sense, this half-plane model is a good approximation to what I have here in the setting of the UIPT. Okay? So again, I have to specify what I have in the holes, because of course my yellow triangles do not fill everything, so I have holes. Okay, for instance, I have this hole here, I have another one here, and so on here. And I say that I fill the holes again by free triangulations exactly as before. Okay, okay, so now my half-plane model makes perfectly sense. So you should imagine that here I have again a triangulation, something like this. I don't know. Maybe that's a triangulation and so on. Okay, so these are filled by free triangulations. Okay, so I repeat, there are two things. First, the yellow configuration coded by these independent trees, and then the holes filled in by free triangulations. Now, what can I do with this half-plane model? Well, in a sense, it's much more tractable than the model here, because there is more invariance, translation invariance, and so on. Okay. So I consider now, okay, all this was did not involve any modification of the distance, but now I am going to consider a modified distance in the half-plane model. So I look, for instance, maybe I can just, I can certainly erase that. I can look at the first passage percolation distance. So consider DFPP. So this is the first passage percolation distance on half-plane model. And I have an easy proposition which says that, well, I'm going to look at the first passage percolation distance between 0 and the line LK here, okay, a line far below. So say proposition 2. Okay, well, I can say that if I look at the FPP between the origin 0 and LK, if I normalize this by 1 over k, this converges almost surely now as k tend to infinity towards a certain constant, C0, which is going to be positive, or it's going to be necessarily, in fact, in this interval. Okay? Okay, so this comes, the proof is quite easy. It's just subadditivity. Okay, so what we say, we just look at first passage per collection distance between, say, the line Lk plus L, and we can bound this by the first passage per collection from the origin to the line Lk plus something which I denote, say, by Zkl, where Zkl is distributed as a distance between 0 and L, and is also independent of the first term here. Okay, so how do we get such a bound? It's actually very easy. You just say that, well, you have your line L0 here, maybe you have your line Lk here, and you have your line Lk plus L, which is here. You take a geodesic for the dFpp distance from the origin, which is here, to the line Lk. So maybe it's something like that. It arrives here. And now, okay, you just say that, well, you can extend the this geodesic by taking a geodesic from this point here to this line here that remains below this line here. Okay, so you forget about everything that is above level Lk. You just take a geodesic in the region between Lk, below Lk, to this line Lk plus 1. Okay? Okay. And now clearly, while the distance between 0 and Lk plus L is bounded above by the sum of these two lengths, and the second one, well, they are independent, well, it's because all the independence properties you have in the model, and the second one has the same distribution as dFpp of 0 Lk. Okay? So you have really a subadditivity property, and then, well, it's a variant of Kigman's theorem that gives you this convergence here. So in this half-plane model, it's quite easy to obtain this information, to derive this constant C0 from the subadditive ergodic theorem. Okay, so now we want to come back to the UIPT. In fact, there is one more ingredient we need. Maybe I can say it very quickly. There is one more ingredient we need, which is, can erase that. The fact that in this half-plane model, the geodesics do not move horizontally too much. Okay. So we'll see why this is important. So I just state the proposition. Take proposition 3 maybe. Well, what we can say is that if we look at the distance between 0 and a point on this line, say at distance k here, well, distance k, the point, say, k0, say, for instance, here, well, of course, essentially the distance between these 2 points is bounded above by a constant times k, okay? It's clear, but in fact, it is much smaller, okay? So the result that we have is, okay, for every delta positive, epsilon positive, say that there is delta positive, such that if you look at k large, if you look at the minimum of the probability, okay, the minimum of the distances, so I look at FPP distance now. Well, in fact, I can as well look at to graph distances, okay, because they are comparable up to constants. Okay, it's not important. The minimal graph distance between the origin and a point of the form J0, so it's a point on the first line here, with J greater than K. The probability that this is smaller than delta square root of K will be bounded above by epsilon. Okay? So essentially, when you are at distance K from this line, the graph distance you expect is in fact of order square root of K, okay? But it cannot be smaller, okay? So this is the meaning of this proposition. You cannot get something which is smaller in comparison with respect to square root of K. Okay, so maybe I have 5 minutes for the last part of the lecture. So now I'm going back to the UIPT. Okay, so maybe just to explain how it works. Okay, so I will use a different presentation of the, well, graphical representation of the UIPT if you want. So I will represent UIPT as a kind of cactus. Okay, so here essentially, you should imagine that we have a picture like this. Okay, maybe that's enough. Maybe this. Okay, so what is the meaning of this representation? So you have the root below, you have infinity somewhere in this part here, and the vertical coordinate in this picture corresponds to the distances, so the graph distances, of course, from the root. Okay. Okay. So, for instance, here you are. Let's say I take k here. So, essentially, the boundary of the hull is going to be a curve like this. Okay. So you see here, for instance, in this representation, you see the difference between the boundary of the hull and the boundary of the ball. With the boundary of the ball, you would also have this and this, for instance. But here, okay, by the definition of the holes, the boundary is just something like this. Okay, so if you want, this represents the boundary of the hull of radius k. Okay, and now what I want to do is I'm going to cut my UIPT into slices. Okay, like this. Okay, now slice like this and so on. Maybe like this. Okay, so how do I define these slices? So for instance, the second boundary here, this one is going to be the boundary of the hull. Well, I take essentially something smaller than k, but I take k minus some fixed constant eta times k. So eta is going to be positive and small. Okay. I do not say precisely how it is chosen, but it's important that eta is chosen independently of k. Okay. And then I continue this way. Okay. So if you want, for instance, here I have the boundary of the hull of radius k minus j times eta k, and here the boundary of the hull of radius k minus j plus 1 eta k. Okay, and so on. Now, essentially what I want to do for each of these slices, I want to evaluate the distance, the FPP distance between a point at the top of the slice and a point at the bottom. Okay, so what we want to get, maybe I should keep that. So maybe I state it a little bit informally. I claim that with high probability, for all, it's very important here that I put all here, vertices here in the boundary of the hull of radius k. So I pick a vertex v here, say. I look at its distance to the bottom of the slice. So the FPP distance between this vertex and the boundary of the hull of radius k minus eta k should be approximately equal to C0 times the width of the hull, eta k. Okay. So how do we get that? Well, if we take a fixed v, well, if we choose v at random, say for instance here on the top, well, essentially what we can say that if we look at a neighborhood of v, essentially this looks like, well, the half-plane model. Okay, so this is really what I explained in the second part. If you use first proposition which was there, near v the graph is similar, is close to the half-plane model. Of course, it's not exactly the half-plane model, because remember we had this. We didn't have exactly independent Galton-Wasson trees. We had this product here, but essentially, well, since in the case of the half-plane model, what I just explained, we have an almost sure convergence. We just need some absolute continuity, okay, to say that, well, essentially the distance between v and the vertex at the bottom of the slide, this will be very close here to half-plane model. If we zoom near V, we see something which is very close to the half-plane model, and we can apply the proposition 2 here. Okay, so essentially we get this by the second proposition. Okay, something which is also important, in fact we also need the third proposition, so I have no time to explain that in detail, but why is this important? Essentially, maybe I don't know if I said that before, but it is known that the boundary here of the hull of radius k has a size which is of order k square. Okay, in fact, if you divide this by k square, this converges to a gamma distribution. No? So essentially what we need to know, we need to avoid the fact that the geodesic for the FPP distance moves too much in the original distance, in the horizontal direction. We need to avoid the possibilities that a geodesic turns around the slice, because then we would not be able to apply the half-plane model. So we need to avoid a large horizontal displacement for FPP geodesics, and this is the reason for this proposition. Okay. So you see this, I should have put here k square and k here, it's just the same. You see that here you need to avoid that on a distance of order k square, well, the distance becomes small in comparison to k. Okay. Okay, so then essentially, I'm going to stop. In each, well, you need one more ingredient. This would be for a fixed vertex V, but there is a way of proving this simultaneously for all vertices V. Okay? And the way we do it is by, in fact, the boundary of the slice, the top boundary is covered by a finite number of balls of radius, say epsilon k, and we can use that to get here the property with all vertices. Okay, so we use this property for every slice, and we just sum the estimate that we get, and in the end we obtain what we want, well, at least for vertices which are on the boundary of a hull. We obtain the fact that the graph distance from the root is a constant times, well, the modified distance from the root is a constant times the graph distance. Okay, but then, okay, there are other arguments to say that this can be extended to all vertices. Okay, but I'm late, I should stop now. Thank you for your attention.
For a couple of more questions. Yes?
So you're saying that for any modified distance, these are never really influenced by the geometry which is above the half plane. Because if I zoom in on one of these points, it's not a half plane, it's a full plane.
Yeah, okay. Yeah, so you say, well, in fact, yeah, you're completely right. Your geodesic here, starting from V, it could well go above first and then down. Okay, so you may think, well, my half-plane model, I do not take into account what's above. Okay, but what is really important is the fact that we have this property for all here, vertices. So if you go above, but at some point you will come down and you will meet another vertex V prime here, and then you know that, well, you need at least that amount of time here to go to the next slice. Okay, so it doesn't really matter if you want. Okay, you cannot get something significantly shorter by going above. Okay, what you get if you spend some time above and come to another vertex will be still at least this quantity here. Okay, so that's the argument here. But otherwise, I agree with you. We should. Okay, it's, of course, a geodesic from V to here is not going to stay above the slice here. So you may think at first that the half-plane model is not the right one, but it's very important that we get this uniformity here.
Questions?
You mentioned quadrangulations, I guess, in the
Yeah.
bijection. So I guess all the methods that are presenting here also generalize to this.
Yeah. In fact, there's also a paper by Krikun, you know it certainly. What he does is kind of layer decomposition for quadrangulations. So it's a little bit similar because what's maybe nicer in triangulations is that on the boundary here of the hull, you have only vertices at distance k. They are all at the same distance from the root. And this is not true for quadrangulations because, well, it depends how you define the boundary, but essentially a quadrangulation is bipartite, so you cannot have edges between two vertices at distance k. Okay, so but still there is something very similar to this layer decomposition, and this is what we expect to use in the quadrangulation case here. We have not written all details for quadrangulations, but it should work in a similar way.
Anything sort of a bit quantitative that enables you to get something more sure rather than quenched? Proposition 3, the limit.
This is in fact a bit difficult to obtain. In fact, this is really a technical point. I should have mentioned probably that this there are other half-plane models for infinite triangulations. Okay, so there is a thing what people call the uniform infinite half-plane triangulation. I think it was first introduced by Omer Angel. Well, it's a different model because it's a model now you look at the upper half plane, but in a sense it's very much, well, you may think it's the same, but well, I should not say that.
Related.
Well, you could of course use a symmetry, but it's not constructed in this way in any case. Okay, but it's related certainly. So in fact, what we did, we proved that kind of estimate in this model, and then we use the relation between the two models to get it in this one. Okay. And in this model, you have a nice peeling process, okay, and of the type that Timothy explained the other day, and you can. Well, this peeling process is it's a powerful tool even for proving such estimates. Okay, and this is what we do. So, okay, we have not thought enough. So another question is, of course, can we get fluctuations in this result or not? And that's okay. Well, we don't know at present.
Okay, so let's thank Jean-Francois again. And,